Right, in this next section, the next video, I'm going to look at 9.1. I'm going to call it Part B. It's just the next couple of pages on after the talk about the muon experiment. Now, the heading I've used in the text is frames of reference. I've got a dot point there because I want to make sure we talk about that and we don't forget. That's the important point. Now, frame of reference is just basically the axes, or it's a set of grid lines, if you like, that you judge all your experiments by, in physics anyway. So in our room, in our lab, that's our frame of reference. And if I was in the lab now, we'd call that the x-axis, the y-axis, and if we ever did three-dimensional work, you'd have the z-axis coming out like this. Now, in senior physics, we only do two-dimensional. Grade 11, or the unit 1 and 2, we just do the one dimension. And if you remember, it was mostly about linear motion along the x-axis, along a road, or we did the dropped ball sort of experiments were vertical motion. So we did horizontal and vertical separately. In unit 3, which is the projectile motion, if you remember, we did projectiles of all sorts of things, and inclined planes, orbits, centripetal motion and things. No, they were in 2 dimensions. But of course you have 3 dimensions, or 3 conventional dimensions. Now, that's our frame of reference. Now, this is how we've often represented it, just x, y and z. Now, if you're doing this experiment, the same sort of experiments at a lab somewhere else, a neighbouring lab, a lab at another school, they'd have the same frame of reference. They'd use x, y and z, and they'd get the same results. So let me just talk about some of the sorts of experiments that you can use that we've done where we've talked about a particular frame of reference. Probably the simplest one was the one we did with the inclined plane. If you remember, we let objects run down an inclined plane and we measured their speed, we measured the angle, and we knew things like the force down the incline was equal to Fg sine theta and all sorts of things like that. Now, if you did that experiment in our lab at school, you get a particular set of results. If you did the same experiment at another lab somewhere at another school, you'd get the same sort of results. Okay, now the thing is, they're our frames of reference. But you could have another frame of reference that's moving relative to this, and you'd get the same results. Now let's imagine you're doing that experiment aboard a ship, and the ship was travelling at constant speed. Now you'd imagine in a classroom on a ship, travelling at constant velocity, I should say, not speed, velocity, so it's going in a straight line, constant speed. That experiment would give you the same results. Just the same as if you did the centripetal motion experiment with the ball being whirled around in a horizontal circle. It wouldn't matter if you did it in your lab at school, at a lab at another school, or on a ship, or even on a train travelling at constant velocity, or a bus travelling at constant velocity. You'd all get the same results. You'd all agree with the aim of the experiment, that in whatever the aim was, Fg sine theta equals the force down the incline and so on. Now, the thing is, I'm saying you'd get the same results if you were travelling on a frame of reference that was moving at a constant velocity relative to you. Okay, now the question about frames of references, or frames of reference, is which is the correct frame of reference? Is the one aboard the ship the correct frame of reference, or is the one in our lab the correct frame of reference? Now, up until about, say, 1900, the Newtonian worldview, that's the worldview put forward by Isaac Newton in the 1670s, was that the Earth is the absolute frame of reference, and we judge everything, every motion, the motion of the planets and so on, relative to the Earth, and there is no other frame of reference. But when Einstein came along, and others, they realised you could have other frames of reference. There was no fixed frame of reference. And, for instance, you could do it aboard a ship and so on. Now, the question about who is moving and who is not moving, is the person on the ship moving? They're in a moving frame of reference. Or are you stationary, or are you moving? Well, the answer is it depends on your definition, or it depends on how you want to define yourself as an observer. For instance, we're all in the same frame of reference at the moment. So if I'm standing in the lab, you would be sitting in the lab and I'd be stationary out the front, and we'd all have the same frame of reference, which is the lab. Now, if I moved past you like this, we would have two different frames of reference. I'd have my own frame of reference, which is moving like this, okay, and you'd have your own frame of reference, which you would say is stationary. You'd say, I'm moving, and I'm in the moving frame of reference. But I could say, no, I'm stationary, you're moving, you're in the moving frame of reference. The question is, who is right? And the answer is, there's no one. Neither of us are right, because it's a matter of how you define who is stationary and who is moving. Okay, so to me, if I do this, if I walk across like that, I'm saying you're moving that way, and you might say, well, but your feet are moving, you've got to move along the floor. And I'd say, no, the earth is rotating under my feet, and I've got to keep doing this to keep from moving along with the earth. So I've got to do this as the earth moves, and so that I don't move along with the earth with you. Okay, so the point of that is there's many frames of reference. There's an infinite number of frames of reference. You've defined the one in the lab as being your frame of reference, and that could be your stationary frame of reference. But I could have my frame of reference. Now, in my frame of reference, I could have a muon. So let's imagine this is the muon, and I'm watching the muon decay. So if I'm travelling along with it, if I had a stopwatch, I would measure, I haven't got a stopwatch, if I had a stopwatch, I'd measure the time for this thing to decay, the muon to decay. So it'd be created now, and then it would decay, and that would be 2.2 microseconds. To you, that would last longer, because you're in a different frame of reference. Now remember, I'm in the frame of reference like the muon coming down from the sky. You're in the frame of reference as the scientists measuring at Mount Washington in the little labs, if you like, at the top and bottom of the mountain. That's your frame of reference. Now to me, I could say I'm stationary and I'm measuring the time for my life, the muon's lifetime, to 2.2 microseconds. You would measure it from your frame of reference and say it's 23 microseconds. It's longer. You measure a dilated time. You'd say my clocks seem to be moving slowly. My clock is only getting up to 2.2 microseconds when yours is getting up to 23 for the same event. And the event is the creation and disappearance of the muon. Okay, so you'd be tempted to say, moving clocks, that's me. Now I believe I'm a stationary clock, but to you I'm a moving clock. I run slowly. So my clock is running slowly. If you keep that in mind, that statement, moving clocks run slow or slowly, we use that later, but you've got to be really careful about how you interpret that. So that's a moving frame of reference. I'm in a moving frame of reference to you. You're in a moving frame of reference to me. Neither of us is right or wrong. They're just different ways of looking at the same thing. Okay, so that's the first point. So all experiments done in moving frames of reference, if they're going at constant velocity, you'd agree. So like I said, the inclined plane, if I did that on a ship, I'd get the same results. If I did, what are some of the others we did? The inclined plane, the projectile motion. That's right, we did the firing the ball across the room. So you'd get, for the same angle and spring value, you'd get the same distances whether you did it on a ship now or in the lab. Or the centripetal force ones, there's three common ones we've done. Now they're all about Newton's laws of motion. F equals ma, the fact that you travel in a straight line unless you're there's a force moving you sideways and so on. So we can say that Newton's laws of motion are consistent between frames of reference if the frames of reference are moving relative to each other but at a constant velocity to each other. Okay, so now we need to get to this idea of inertial frame. Now if you were doing an experiment, say in a car, now let's imagine you had something hanging up. Say you had a pendulum hanging up in a car and you're both at rest, so people on the side of the road and people in the car looked at the pendulum, and you could actually measure the time for the oscillation of a pendulum. Now if you accelerated, what would happen is, if you watch this ruler, when I accelerate, the ruler comes back. It looks like there's some force acting on it. Now there's no force, it's just that we're in an accelerating frame of reference. Now if you tried to measure the time of the period of a pendulum in an accelerating frame of reference, you'd get results that didn't agree with the results when you did it in a stationary frame of reference, or one moving at constant velocity. Now we would say Newton's laws of inertia, which were the laws of the first, second and third laws of motion, don't make sense in a accelerating frame of reference. Okay, so we have to define an inertial frame of reference. Now when I'm travelling at constant velocity, or if you're stationary with respect to another frame of reference, you say that's an inertial frame of reference. Now an inertial frame of reference, simply in the syllabus it just says it's not accelerating. Okay, so really you could learn it as an inertial frame of reference is one that is not accelerating, but you should look at the exact definition in the textbook or in the syllabus if you like. They're pretty much the same. So basically inertial is not an accelerating frame of reference. So if you drop a ball and it accelerates towards Earth, you're in a constant velocity, you're in an inertial frame. Anyone travelling along with the ball would be in a non-inertial frame of reference. So what you'll get on a probably a multi-choice question on an external exam would look at which one of the following is not an inertial frame of reference, and it would give you examples like driving around a corner in a car, and of course you're changing your velocity, the direction of your velocity, so it would be accelerating. Starting off in a lift and going upwards, you know, an elevator going upwards, that's accelerating, and things like that. So wherever there's acceleration going on. Now you could get into, if you read a lot about this, you'll find out that definition could be improved, but the syllabus has gone for a fairly straightforward definition, and that's all you'll need for the external exam. So I wouldn't try and get too involved about, you know, if you're travelling along with a ball as you fall down, you know, are you accelerating or is the observer in the lab accelerating? Don't worry about that. Just think, if the object is accelerating, as far as you're concerned, it's not an inertial frame of reference. I think we can leave it at that. That's the main point for frames of reference. And I'll go on and look at Einstein's special theory of relativity in a minute. That'll be 9.1c. That's the two postulates. Okay, we'll leave it there.